So let's finish up this video. We talked about, in part A, how we're going to solve conservation of energy problems by using this equation here that shows that mechanical energy is conserved. So let's look at this example. We have a child is starting from rest, sliding down a water slide. There's no friction here. The top of the slide is 3 meters above the ground, and the bottom of the slide is 30 centimeters above the ground. What is the speed at the bottom of the slide? So first you need to realize that this is a conservation of energy problem. There's no friction. The girl is losing height and gaining speed. So then we're going to write down the conservation of energy equation. 1/2 mv initial squared plus mgy initial plus 1/2 kx initial squared. And really, you don't have to write that third term if there's no spring in the problem. I'm just writing it to be complete here so that it matches up with the equation I showed you on the previous slide. So plus 1/2 kx final squared. So you write down the equation. This is your initial kinetic energy, your initial gravitational potential energy, your initial spring potential energy, and then the final energies. So now let's go back to the previous slide. It said, well, identify the zero level and the givens. I forgot to do that. And then we're going to cross out all the terms equal to 0. So the zero level is the lowest point in the problem that you care about. So in this case, the bottom of the slide is 30 centimeters above the ground. So if I were to draw a picture here, it's kind of like this, right? The ground is here, but we're given this distance here of 30 centimeters from here to here, and then the distance of 3 meters from here to here. But we don't care what happens at the ground, we only care what happens at the bottom of the slide. So we're going to call this the zero level. This is going to be y final equals 0. That's where she gets to, that we care what her speed is at this location here. So that means her y initial is up here. So I'm not going to use 3 meters for the y initial because it's the position relative to the zero level. So if you can figure out what this distance is, if this is 3 meters and this is 30 centimeters, which is 0.3 meters, then hopefully you can see that y initial is 3 minus 0.3, which is 2.7 meters. So I'm just defining my position relative to my zero level, which is right here. So that's 2.7 meters from here to here. So now I'm ready to, let's write down any other givens. It says that she's starting from rest. So that means v initial is 0. And to be honest, sometimes instead of writing that down, I'll just go straight to my equation. You notice I wrote my equation first. Go straight to my equation and say, okay, well, v initial is 0. I'm just going to cross out that whole term that's equal to 0. And then I just keep going through each term and seeing what's equal to 0. Y initial is definitely not 0. It's 2.7. So I've got to keep that term. There's no spring, so that's 0, no spring energy. V final is not 0. That's what we're looking for. What's the speed at the bottom? Now, the final potential energy gravitational here is 0 because we set the y final to be 0 at the bottom of the slide. So if y is 0, that means mgy is 0. There's no spring, we cross out the spring energy term. So what looks like a complicated equation only has 2 terms left. And now we can solve for v. So we have mgy initial equals to 1/2 mv final squared. When there's no spring potential energy, all the other terms have mass in them, so they can actually cancel out because they're in both terms. And to solve for v, we're going to multiply by 2 to get rid of that y, of that 1/2. And then that's equal to vf squared. Then we're going to take the square root to get vf by itself. And now we can plug in the numbers. So the numbers that you have to plug in is the square root of 2 times 9.8 times 2.7 was our initial height. Plug all of that in, and I got 7.27 meters per second. So that's our final answer. Let's do one more question in this video, this your turn question. So we have frictionless slides. So again, we're just not dealing with friction quite yet. We'll get to that very soon. A small child slides down to 4 frictionless slides. There's 4 of them here, different shapes. Rank in order from largest to smallest the speed at the bottom. So you may think, oh, well, D is steeper, or you may think, whichever one's steeper, she's going to go faster on that one. But remember conservation of energy. If there's no friction, then that means that the initial energies equal the final energies. So I'll just write KE initial plus PEG initial. I'm not going to worry about the spring. There's no spring here. Equals KE final plus PEG final. So we're going to assume, let's assume that she starts from rest in all the cases. Because of course if she started at different speeds, then that would affect the speed at the bottom. So let's assume all the speeds are the same and she starts from rest. That means there's no initial kinetic energy. Let's call that bottom level here y equals 0. So whenever she gets to the bottom, she has no potential energy. PEG final is 0. So what this means, conservation of energy, is that all of her initial gravitational potential energy, mgy, initial, is converted to kinetic energy. So she has the same exact height at each different slide. You can see if she has the same height, she has the same amount of potential energy at the beginning. That means she's going to have the same amount of kinetic energy at the end. Since it's the same person sliding down a slide, she has the same mass, which the mass cancels out anyway. But this means that her speed is going to be the same at the bottom of each slide because she started from the same height each time. So just to recap, conservation of energy, we're going to see it more in the next few videos, but you just have to write down the full equation and cross out the terms equal to 0 and know that energy is just transforming from one form to another. No energy is lost.